The diagram shows a cell in series with a 45 ohm resistor. When the switch is open, the voltmeter reads 2.0 volts. When the switch is closed, the reading falls to 1.8 volts. Determine the EMF and internal resistance. So of course there's some internal resistance. The first thing I do is draw that on, which will help me visualize. Okay, so when the switch is open, just like as is shown here, the voltmeter is reading 2.0 volts. Okay, so what's going on? So when you have an air gap, this is what the switch is, it's just an air gap, isn't it? So we can assume that the air has very high resistance. I'm going to pretend that it's got very infinite resistance. So when it's got infinite resistance, firstly there's going to be no current flowing in the circuit. That's quite important. And also all the potential difference is actually going to be across the open switch. Okay, just because all the potential difference is across the open switch doesn't mean there's any energy being used across it or there's any current flowing through it. It's just, you can think of it as having taken up all the voltage because it's got the highest resistance. Okay, then the next thing to note is that when this is happening, when the switch is open, the potential difference here across the terminals is the same as the potential difference across this power supply, the cell. So in other words, when there's no current flowing in the circuit, the current is 0, the terminal voltage is equal to the EMF. So in this question, this first sentence tells us that the EMF of this circuit is equal to 2.0 volts. Now that we've got the EMF, we can figure out the internal resistance. We're going to use this information here, that when the switch is closed, that the voltmeter reads 1.8 volts. So what's going on? So the reason why it's fallen is because some of the energy is being used inside the cell now. Now that there's a current flowing, there is going to be some lost PD. And the lost PD is going to be 0.2 volts. Okay, and the remainder, which is 1.8 volts, which is the terminal voltage, and that's being used across the load. Now if we look at this very carefully, we know two things about the load. We can work out a third thing, which is going to be the current. So 1.8 volts divided by 45 ohms gives me the current in the circuit, which is 0.04 amps. Okay, that's flowing around, and of course that current is flowing through the internal resistor as well. So the current through the internal resistor is 0.04 amps. Now that I know the voltage across the internal resistor, or the lost PD, and I also know the current, I can work out the internal resistance. So 0.2 volts divided by 0.04 amps will give me the internal resistance, which is 5 ohms. Okay, the cell in the circuit has an EMF of 2.0 volts. So I'm going to go ahead and add that onto the diagram here. Okay, supplying 2.0 volts. When the variable resistor has a resistance of 8.0 ohms, the potential difference across the terminals of the cell is 1.6 volts. Okay, straight away I know that means that the lost PD is 0.4 because it needs to add up to 2. Okay, what is the potential difference across the terminals of the cell when the resistance of the variable resistor is increased to 14 ohms? Okay, right, see the second part of this question here, number 2, I'm changing the resistance, so it's going to change the lost PD and the terminal voltage. So I'm not going to do that just yet. I'm going to use the first part of the question to figure out important information, which I can use in the second part. So in this case, I'm going to use it to figure out the internal resistance. Okay, so straight away I know that there's two pieces of information over here. The voltage is going to be 1.6 and the resistance is 8, so I can figure out the current in this circuit here. Okay, so which is going to be the same throughout. So the current is going to be 1.6 divided by 8. That gives me 0.2 amps flowing. I know that 0.2 amps is going to be flowing through this internal resistor as well, so that means I can work out the internal resistance. So 0.4 volts divided by 0.2 amps gives me an internal resistance of 2 ohms, which sounds about right. Okay, so now I'm going to use that for the second part of the question, because the internal resistance is going to change when I change this here into 14 ohms. But all of this, everything else is going to change. The lost PD, all of this will change. Oh no, the EMF won't change though. Okay, so the internal resistance now is still 2 ohms. Now we have 14 ohms here. Okay, so what do we have? Well, we've got the total resistance. So the total resistance is going to be 14 ohms plus the 2 ohms, that gives me 16 ohms of resistance. I've got the total voltage, which is the EMF. So I'm going to do 2 volts divided by the 16 ohms. That will give me the current in the circuit. So that gives me 0.125 amps flowing in the circuit. So you can see the current has decreased from 0.2 to 0.5. That makes sense. Now that current is going to flow through the load as well. So it's going to flow through here, 0.125 amps. So that means I can work out the terminal voltage when I've changed it to 14. So V equals IR, so V is equal to 0.125 times 14. That gives me 1.75 volts. So we can see the terminal voltage has increased, and that means that the loss PD has decreased. So now the loss PD is 0.5 volts. And that's what we expect. We expect if we increase the terminal, the resistance of the load, it gets a larger fraction of the total potential difference.